Sorry, I just turned on the microphone now, so you missed something, but it should be fine. Those watching the recording, I apologize. Anyway, so we know that this, if I look at R equals n divided by 2, I can also see the same power law decay as if I look at finite R in an infinite size. So the thing is, and I will talk more about this later, the Heisenberg chain is sort of a slightly contaminated CFT. What? Is it too loud? Maybe I'm just too loud. Maybe I take this. Is it better now? Right. Let's see. Hello, hello. Is it okay? All right. Okay, so in terms of CFT description, this model is slightly contaminated. I will discuss it more later, but it's basically there's a marginally irrelevant operator there, which is known to cause this logarithmic correction. So everything is known about this model, but let's just see if exact diagonalization can capture it. So since we expect the dominant decay to be 1 over R, here I have a well, there's some dirt there, but C of R times R. So that should be flat if it's really 1 over R. And you can see it's not quite flat. So these are for different system sizes as a function of the distance, and there's some even odd oscillations there, which are known. In the lattice, all kinds of things can happen, right? But you can imagine that this comes from the log correction. Now the red points here, those are if I look at R equals half the system size, and there it's much flatter but still slightly increasing. So you can see that it's not easy to study this form here. One needs to go to much larger systems, but at least it shows something along those lines. Now if you do quantum Monte Carlo simulations that I will start talking about probably tomorrow, you can go to much larger sizes and really see this quite nicely. I mean, you can fit to the logarithm and so on. And you can also do DMRG, which I had planned to talk about, but probably I don't have time to talk about. And anyway, the log, as I mentioned, comes from a marginal operator. I will say a bit more about that. Now you can also, with this Lanczos method, as I explained yesterday, you can look at the excitation. So here I just show some examples of the excitation gaps. The ground state is a singlet, and here I show as a function of the momentum the spin 0, 1, and 2 lowest excitations, and you can see that they form this they come close to this curve here, which shows the known form from actually the beta ansatz solution of this model. So since the size is finite, we have some deviations, but at least over here it's quite good. And in the thermodynamic limit, since this model actually has spin-on excitation, so you have a pair of spin-ons, and they just fly around pretty much independently, and you in fact have a continuum of excitations of singlets and triplets, in some regime here. I will show some experimental results in a moment. But one point is that the singlet and the triplet, they should become degenerate and both fall on this curve in the thermodynamic limit. And you see here they are at least close to each other. So what are these spin-ons? So just this is a cartoon picture. I stole it from a paper that I will cite in a moment. Everybody uses this kind of illustration of what spin-ons are. And there you start from something which is not the real ground state of the Heisenberg chain, just to make it simpler. Let's start with an Ising antiferromagnet, like here, up, down spins. And then you imagine that this Icing chain also has some quantum fluctuations in it. So what happens if you flip one spin? That's sort of almost like creating a spin 1 excitation, although it's more like an SZ1 excitation. So then you see you have an energy mismatch here indicated by stars. So you have two bonds where the energy is no longer minimized. But now in the Heisenberg model, you have these, off-diagonal spin flips, pairs of antiferromagnetic spins can be flipped. So if you think of a highly anisotropic situation where the model is almost the Icing model, but you have added a little bit more of this XY term, then you can flip pairs of spins, by the Hamiltonian in, let's say you do time evolution. And then you can see that, you cannot flip these two because they are parallel, but you can flip those two, or you can flip those two. So if you do, either of those, in this case on the left side, it's like you move this mismatch of you move the bond where the energy is not minimized. So now you see that you can continue that without increasing the energy anymore, right? After you have done the initial flip, these additional flips don't cost any energy. So it's like, and these are domain walls, right? So the domain walls are what we call the spin-ons. And in reality, if you have a lot of diagonal term, the domain wall will be not just a very, very local thing, but it will be more spread out. And in fact, in this actual Heisenberg chain, where this is very far from the true ground state, which only has, is only quasi-ordered, the spin-ons are very, very broadened out. If you look at them in real space, they're sort of marginally, localizable particles. Anyway, so one point is that this kind of thing one can see experimentally. So here I just show some experimental result. This picture is also from this paper, and you can see this is my lowest excitation here from k goes to 0 to pi. Here it's plotted, from I guess the units are different. So my 0.1 here corresponds to 1/2 here, so they divided by 2 pi. And you see that these two arcs here, like here it's most clear. These are different temperatures. So let's just focus on this one. So you see that there's a lot of, well, okay, what is this? It's neutron scattering. So let's not worry where it, exactly how that is, how that works if you don't know about it. But basically it measures the spectral function of the SZ operator, let's say. Which has support in some region here shown by this coloring here in the experiment, where these spin-ons give spectral weight. So the arcs here, the black solid and dashed curves, those are the theoretically predicted regions in momentum energy space where these spin-ons should show up. So this is sort of a confirmation that one can see this kind of one-dimensional physics experimentally. Okay, so let me now go to another deformation of this Heisenberg chain. Let's look at the J1, J2 model, where you have the nearest neighbor interaction that we had before, but now you also have second nearest neighbor interactions. So you can think of that as a chain, and you just have a longer range coupling J2 as well. But you can also think of it as this geometry where you have two chains, and this is the nearest corresponds to J1, which is like the nearest neighbor coupling here, and then you have these blue ones, which are the connections in these two individual chains. It's just two ways to visualize the same kind of connectivity that you have with these couplings. So an interesting thing here in this model, this was studied in the 1960s already by Majumdar and Ghosh, and they found that there's one point where the ground state can be found exactly here, and that's when this coupling ratio is 1/2. Then it turns out that you have two degenerate ground states, which are these singlet product states. So these are dimerized states, and you can dimerize in two different ways. And this again, illustrates, singlets, as I discussed before as well. So it's actually super easy to show that these are eigenstates. You can just, they are even eigenstates of just, one J2 coupling and two J1 couplings locally. If you just, or maybe just one of each, I forgot now, but there are eigenstates of all sort of local interactions. So it's a sort of very simple ground state. And you may recall that in the first lecture I talked about what's called the Shastra Sutherland model, which I will return a little bit to today, where Shastra and Sutherland were motivated by this result to construct something similar in 2 dimensions. So these are exact ground states, and then they're really exactly degenerate, meaning any superposition of them would of course also be a ground state. But then what happens if you go away from this point? Well, we know for J2 equals 0, it's just the Heisenberg chain we just discussed. And it turns out that, well, this is a gapped state, with long range order. So if you just
and there is a question.
Yeah, please.
Just a small question. So I can understand it being an eigenstate, but how do you know it's a ground state? Like, is that also simple to see?
Okay, so how these are ground states?
Yeah.
Okay, just take, I think if I remember correctly, you just take somewhere in the chain, you have J1 and you have J2. Just take those 2 operators, the Hamiltonian is a sum of all those, right? But just take those 2 and operate on these states, and you will see that because of some cancellation effects, you get the exactly the state back, right? So these operators, of course, will, if you work in this basis of singlet of singlets, there's some very easy rules for what happens if you act with S dot S on a singlet. This is basically an eigenstate of S dot S, right? But if you act between, you will actually reconnect the singlets in a way, and that's if you know those rules, it's very easy to show that these are ground states. But even if you just write the singlets down in the Z basis and just trivially act with the Hamiltonian, it's sort of a 5-line calculation to show that. So you can try later and show me and ask me if you have any problems with it. So the point it's sort of the beta ansatz, which is used to solve just that part. That's something horrendously complicated, right? But this is something super easy. So I guess it was maybe not easy to have the idea to do it, but once you know the answer, it's very easy to confirm, right? XXC is also solved with the beta ansatz. I don't think this model, maybe I don't remember, but I don't think so. But I'm not 100% sure that if you can make it anisotropic and there's still a solution. I sort of don't believe that, but I'm not 100% sure. All right, so what happens? Yeah, okay, so the point was if you perturb just a little bit away from this special point, it's clear that dimerization should survive. But then we know if you go closer to the single chain, if J2 becomes very small, then it should become closer to what we had, this critical ground state. So in fact, what does happen is that for the coupling ratio being larger than 0.24 and up to something like 0.6, this kind of order survives. These are no longer exact eigenstates, but that kind of dimerization will survive. So it has a broken, in the thermodynamic limit, the symmetry will be broken. Whereas below that point, you have the critical state, which is very similar to the chain with only nearest neighbor interaction. So in fact, you have a critical phase going to a dimerized state. And exactly where the dimerization happens, which has been determined numerically, and I will show you how in a moment, at this point 2, 4, 1, 1, there this system is a sort of clean, has a clean CFT description, and the CFT is in fact the K equals 1 Wess-Zumino-Witten theory, which all of you probably know more about than I do. the reason that before that we saw this log correction is because that CFT contains, well, so this chain, this Heisenberg chain contains an operator that is marginal in the CFT, and it's marginally irrelevant, for smaller than this ratio, so that causes the log correction, and it's marginally relevant in this phase, and that's what causes the symmetry breaking on that side. So there's a marginal operator which changes its sign as you go through the point. Yes, please. Yeah, it's SU2, level K1, I guess you call it. Yeah, I should have said SU2. Yeah.
So there must be some, as a numerical way, what would it be? So say you take the Hamiltonian and diagonalize it and see. So what would your method be of seeing whether this CFT would it be?
Okay, yeah, good point. So I happen to sort of remember that because my student Pranay Patil, who's maybe there in the back, we had a project with my colleague Ami Katz, who's a field theorist, and he's in this Simon's bootstrap collaboration as well. So from that, I remember that you have to map it to fermions, then you see it. Isn't that right, Pranay? Right, but to show that it's a CFT, exactly, you map it to fermions, right? And then it's actually to free fermions even.
That's analytically. That's
yeah, exactly. So it's for people in this game, it's actually not hard to show that it's described by this CFT.
And numerically, so if you were suppose you were given a spin chain for which you cannot do an analytical mapping, how would you numerically show like? I guess there would be no short way of saying it's a CFT.
Yeah. So if you cannot show it analytically, I guess for these spin chains, so much is known from CFTs that you can pretty much nail down from symmetries what it should be, and then you can test it numerically. I will show some of these tests today, but there are predictions for how the gap should scale with the system size. Other things that I will show you today. So I will talk a little bit about that. But yeah, that's of course an important thing that if you cannot show it analytically, but you can sort of test things numerically. Okay, so
all right, one more.
Yeah.
So at J1 or J2 probably equal to 0, you still get SU2 level 1, right?
Yeah. So for all points up to this point, it's that CFT, but that marginal operator is present there and will cause log corrections. But if you go exactly to this point, that log correction that I showed you before, well, let me go back here. This log correction actually goes away if you go to that special point 2411. So if you want to confirm the CFT, it would be best to go to that point.
Are coupling J2 over J1 marginal here?
Well, you can say that the coupling, J2 over J1 drives the strength of a marginal operator, right?
Right. So, but somehow you're starting at SU2 level 1, and then you end up back at SU2 level 1. Yeah,
because the whole phase is described by that, right? It's not just a critical point; it's a whole critical phase described by that point.
Okay. Oh, so
well, the theory doesn't change, but the strength of this marginal operator changes because the coupling ratio somehow, in some mysterious way that I don't know, will maybe when from the CFT mapping you can see it, but I'm not even so sure about that. But anyway, this is work that goes back to Ian Affleck and Haldane in the 1980s and 90s, where they showed all this. So I'm not an expert in the CFT, so I can probably not answer your question properly. But what I do know, the lingo is that there's a marginal operator whose amplitude sort of changes sign when you go through that point. All right, we can discuss maybe more after, because since I'm not even an expert in the CFT anyway, I should not probably say too much. But I will say a few more things about how you can relate. So one interesting, well, okay, so this is an example of translational symmetry breaking, right? But if you take a finite system, at this point, these are both degenerate, right? So then you can say, okay, any superposition of them is also degenerate. If you go a little bit away from this point, but still in that phase, then you have two ground states, but they are not exactly degenerate anymore, but they do become degenerate in the thermodynamic limit. And you can sort of think of states that are superpositions of these. So the actual ground state will be at some momentum 0, and it will actually be like the superposition of these two with some domain walls and stuff in between that allows the system to fluctuate. So for a very large system, it will become more purely such a superposition, and you can really break the symmetry in the thermodynamic limit. And then there will be an excited singlet, which is like this phi a minus psi a minus psi b. So you have an even odd combinations of those, but they are split by a small gap in a finite chain. Right, so numerically, how do you detect such order? Because numerically, when we work on small systems, we don't break the symmetry, right? So you cannot just see the dimerization, at least not in your periodic chain. If you take an open chain and treat the boundary conditions in the right way, you can see sort of dimerization, but it may not be super clear. But what you can look at is what we call a dimer correlation function. It's just s dot s at some location times s dot s some distance away. So it's a 2-point function, although it has four spins. So that correlation function will show an oscillation, and you can see here, g equals 0.4 is inside the dimerized phase. So you see there you get that very strong correlation that doesn't seem to decay away. So the order parameter is basically different, even odd difference here. So it will always have an even odd oscillation if you have something like that, even if you have a superposition of those. And then as you go to the Heisenberg chain, you see that you have much weaker oscillations, but you still have some. And if you go to the critical point, where the dimerization happens, it looks like that. So if you look at one possible order parameter would be take the difference between the even odd at the largest two distances, and then you can see if you can detect the phase transition there by looking at different system sizes. So here I show 3 different system sizes. If you go to this Mashum-Dargosh point where these are exact eigenstates, you can see that all these system sizes, the value is exactly the same, and that's because these are exact eigenstates on all ground states on any system size. But then as you go to larger G, eventually some strange things happen, because this will not be some spiral states and things like that will appear here. So let's not discuss that. But the transition should happen here, and that you don't see very clearly, right? You can say, okay, here it still looks like you have order, this has converged, but here, even if you analyze it carefully, it's not so clear numerically, just based on these results to say where the transition happens. So you would need to go to much more, much bigger systems to actually see the order parameter, going to 0 below this point and being finite above. But there are other ways to analyze the transition, and that's by looking at level crossings of excited states. So that's what I want to show to you, because it's something that may be very useful also in higher dimensions. So that was there another question?
Do you know the reason why it's hard to detect the transition?
Yes, it has to do with the fact that the transition is driven by this marginal operator. So it only induces very weak order, close to that point. So what actually will happen is that the excitation gap as well as this order parameter will only open very slowly here. It will not be a power law. Normally at critical points, you have, some power law onset, but in this case, it's like an exponential thing, and it has to do with the fact that it's driven by this marginal operator in the CFD.
I see. So all marginal operator driven translation have this kind of features.
Right. Yeah.
So how did we, I may have missed this, but how did we know the value of the critical point because
exactly. So that's what I'm going to talk about now. So there's an amazing thing. So first I wanted to show you that it's very hard to see it in the order parameters because of this, driven by marginal operator. But let's look at it in another way. So I showed you these excitations of the Heisenberg chain, right? And if you look carefully here, you see that the lowest excitation for each K is a triplet. The singlet and the S equals 2, they are, slightly above. There's some weirdness happening for small momenta there. Let's not talk about that. Okay, so what happens? So that's something we can say about the Heisenberg chain, that the lowest excitation is a triplet. The ground state is a singlet on a finite lattice. So what can we say about this kind of VBS? Well, these are both singlet states, right? You haven't broken any valence bonds, when you go between these. So you have two not exactly degenerate singlet states in a finite system, but you have two singlets that basically come exponentially close to each other as a function of the system size, if you have that kind of long-range order. So that means, inside the dimerized phase, the lowest excitations of the ground state will be a singlet. Whereas in the Heisenberg chain and, in that whole phase, the triplet should be the lowest excitation. And I think that can also be understood analytically, although I only show you the numerics here. So then if you look at these excited states as or excited energies as a function of G, the coupling ratio, you see this is the ground state, the black solid line, the ground state energy. And then we have the singlet and the triplet energies at K equals pi, where they are the smallest. So these are the two lowest singlet and triplet excitations. Then you see that they cross each other here, and that's very close to this point where the transition happens. And in fact, if you look at that crossing point as a function of the inverse system size, or in this case, it's better to look at it as a function of the inverse system size squared, you see that these fall on a line, very beautifully, right? So, so what this shows is, at what point these cross each other. You see, it's around, 0.24 as a function of the inverse system size, and it's an almost perfect 1/n squared behavior. Okay, so this can actually be explained in CFD, but I would not be able to tell you how. And in fact, I don't really even have any good reference for it, because typically papers, using this kind of methods just said that this is sort of known, but I haven't found any paper that actually explicitly states how, in what way it's known, but it may be something easy for, CFD experts. I don't even know exactly how you put the, well, I guess there's nothing wrong with putting the CFD on a finite system, right? And seeing how the energies go. But so maybe one of you at least will be able to tell me. But let's not exactly worry about, where the prediction comes from. But in any case, you see that this is very easy to do, whereas from the order parameters, it was very hard. And in fact, if you do the extrapolation here and, analyze, your extrapolation carefully, you come to this amazingly, precise number here, where the 2 is the uncertainty in the last digit. So that's quite remarkable. So even though this marginal operator is responsible and causes this rather weak ordering close to the transition in the order parameters, these excited states have a behavior that can be exploited very nicely. Okay, so then universality, right? So this kind of transition is actually quite common. The transition from this Wessumino-Witten theory where there's a marginal operator causing log corrections to where it dimerizes, it happens in other systems. For example, we talked about the JQ model a little bit the first day. One can formulate that in 1D as well, and that has exactly this kind of transition as well, including this kind of point that you can find using level crossings. Also, if you include phonons, meaning essentially lattice vibrations in your Heisenberg chain, if the phonon coupling is strong enough, that also causes dimerization, and exactly the same thing happens there. So it's quite common in one dimension, and this is the paper that I mentioned that Pranay was doing on studying some aspects of CFT like emergent O4 symmetry numerically to see how it happens as a function of the system size. So if you're interested, you can read that and talk to Pranay about it. Okay, let's see. So when should we end again? Like 10 minutes from now, I guess. Yeah, because we started a bit late. So I think I can still finish this part of the lecture today. So let me talk a little bit about what we can do in 2 dimensions, which is of course much harder than 1D, because what we normally do in finite size scaling is we consider the system length. Right, so in 2D, the system length, if I have access to, let's 40 spins, the system length is 6 or 7 or something like that. So it's very small, but one can still do something. So we can again exploit symmetry. So here I illustrate some translational symmetries that we can use to construct momentum states. We can, for some momenta like 0, 0, and pi, pi, we can further, divide up our big matrices using reflection symmetries and so on. So I'm not going to talk about the details of that, but just show you a table here.
Anders,
Yeah.
What was the dimension of the chain before? I forgot.
The largest chain I looked at in the previous graph had 32 spins, and it's possible to go a bit larger, but 32 is something you can do on a laptop computer easily. Okay, here I show some sizes of the Hilbert space in 4x4 and 6x6 square lattices, and this is again in the 0 momentum sector that contains the ground state, and MZ, the total magnetization, is also 0. And here we have some, these reflection quantum number and spin reflection quantum number. And in some cases, one can also exploit this, diagonal reflection at the same time as PX and PY, but not always. So you see, 4x4 is very easy to do because the blocks are very small. But look here, 15, 16 million states, and in this sector, even 31 million states. So that's doable, with big compute. Well, even with not so big computers these days, but it's not super easy. So let me talk about some aspect of the excitation spectrum of the 2-dimensional Heisenberg model. So this is some relatively famous things going back to Phil Anderson in the 1950s. So he came up with this picture to explain symmetry breaking. You know, when you have O3 symmetry of the Nell order, you know, you have a direction and an amplitude of the order parameter. And in a finite system, you cannot break the symmetry, right? But how can you break the symmetry in the thermodynamic limit when the order parameter is O3? And in particular, well, I mean, in principle, that's easy, right? Well, the fluctuation of the direction of the order parameter becomes, you know, less and less as you increase the size, and eventually just locks because the time scale of rotating this vector becomes slow. But in detail, how do you understand that in an antiferromagnet, which has a singlet ground state? So yeah, so the singlet is always a unique ground state on any finite system. So, you know, there's no direction of the order parameter in a singlet state, right? So how do you actually break the symmetry? So he came up with this picture. So let's take a bipartite lattice where, you know, red and white correspond to the A and B sublattices. And then you think of, okay, if you have order there, it's like you have two big vectors, you know, of order of n, spin of order n, and they are coupled to each other in some way because, you know, the two sublattices have the spins pointing in different directions. But you cannot say, you know, what direction this thing as a whole points in. And you can say, well, they are coupled with some effective coupling. We don't know what it is, but we suspect that these spins should be some big spins of order n because they represent, you know, some order in half of the system. There's some, you know, factor of n, but that can be absorbed into the coupling J effective. So now you can solve this system exactly, right? You have two big spins coupled in this way. You can actually find the eigenstates. And in fact, you can also compute some you know, other properties. So you can compute the energy spectrum, right? But that will depend on J effective. So there's some uncertainty there. But you can also compute some other physical quantity that you can use to eliminate JF and instead, you know, get some physical quantity there. So you can express, it turns out, so the ground state of this will be a singlet. And then, you know, you have spin S excitations, which have, you know, forms exactly like this relative to the ground state energy, where, you know, this chi here is the uniform magnetization, uniform magnetic susceptibility of the system defined in this way, just dMdH, where you imagine adding a magnetic field to your Hamiltonian. So in principle, you can test that or even exploit it by saying, well, if that's true, and if I can calculate these gaps, so the gap is just ES minus E0, that gives me an estimate of, well, let's say the inverse susceptibility. So for each n, you know, I say ns here, but it should be just be the system size n here. So for each system size and each s in principle, but you should probably look at as small s as possible. Like here I show what momenta you have there as well. It's not so important. So here's an example of that. So as a function of s, you can form this estimate of 1 over the susceptibility. And you see that it's roughly straight lines here as a function of s. Sorry, it should not be really straight lines. It's some, you know, second order in s. They do have some curvature, I guess. And then, you know, this for small s, that should be an estimate of your susceptibility. Now, this has not converged yet, but you see this is 14 here, 15 and a half. So they're pretty close to each other. If you do this for bigger and bigger systems, eventually it would converge. And then, you know, there are some other ways of computing the susceptibility, so you can check if they agree, and they do. So this is an important aspect of the energy spectrum of the Heisenberg model in any dimensionality higher than 1. You can also try to check if you see evidence of long-range order there by looking at the spin-spin correlations. I guess I say that here. So C of R is just the spin-spin correlations with this minus sign, the oscillation taken out for the two system sizes as a function of R. And you can see that it sort of tends to a finite value, which would be the order parameter squared in the thermodynamic limit if you could continue this forever. Now, the dashed line is the value that's actually known from quantum Monte Carlo that I will talk about later. But you cannot, I guess, say reliably from these small sizes that you have a long-range Nell order, but there's some good indications from from these calculations. Now let me just say, okay, I have 1 more minute, so let me just say something very quickly about this topic. So we have actually used this recently to, this level crossing method that I talked about in the J1, J2 chain. We have used that to try to see what happens in the Shastra Sutherland model that I talked about the first day. I should have repeated the Hamiltonian here, but it's the one where we have nearest neighbor interactions everywhere, and then we have, which is partially hidden here, we have these diagonal couplings in some places. So in that case, we can say, well, there could be this kind of plaquette singlet solid state where you form singlets in a twofold degenerate way. And we know that they can be antiferromagnetic order as well. So we can look for gaps there, and then we can look at gap crossing points. We can identify crossing points, and we can argue, that some phase should be, the end point of some phase should be characterized by one level crossing, and the starting point of some other phase should be governed by some other level crossing, and so on. And without going into details, let me just say that we, Ling Wang, she did these calculations up to 36 sites, 6 by 6. Yeah. Okay, so let me do what I skipped there then. Yeah. So there are some assumptions. So let's see. So one criterion for the plaquette singlet solid state is that it should be a twofold degenerate state. Okay, so then in that phase, the singlet excitation must be the lowest because you have two quasi-degenerate singlets. So the second singlet that we calculate, this one is the ground state. The second singlet should be below the first triplet excitation. So this is some example of what the levels may look like, but it's just a cartoon. So if you have that kind of doubly degenerate ground state with a triplet excitation, then this must be true. Okay, if you have antiferromagnetic long-range order, then you should have this Anderson rotor states as the lowest excitations. So that will mean that this quintuplet that we are looking at, the S2 state, should be, smaller than your second singlet state, because the second singlet should not be part of the tower. It should, in fact, according to well-known people, describe the amplitude mode, which is gapped in the you can call it Higgs, but it's a slightly wrong term. So you can use that as the criterion for an antiferromagnetic state, and you can also argue about some other crossing points more inside this whole thing here, not relative to the ground state. So in that way, if you see that these levels cross each other, you can say, well, that must be where the antiferromagnetic phase ends, right? And when you see these levels cross, that must be when the plaquette singlet state ends. So there's no doubt that the plaquette singlet state exists, the antiferromagnetic state exists. The question is, how far do they go? Where do they connect to each other, or is there something else in between? And in fact, what we are seeing, and this is now, if we have just 4x4 and 6x6, it's not enough to try to do some scaling. So one can do these, tilted lattices and non-square lattices and so on. And we get some, levels or gaps, I should say, as a function of G, which is again a coupling ratio. And then we can see how those couplings move as a function of the system size. And let me just say that the most important thing here is these two seem to extrapolate to different points. So that one will indicate the end of the plaquette singlet state, this one, and the other one will indicate the starting of the antiferromagnetic state. And what people have believed is that, those should transition into each other at one point. Now, this seems to suggest that they don't, but of course the system sizes are small. But we can actually, and you see there's some annoying oscillations here which have to do with the different cluster shapes. But you see that there's some correlation in the way that these oscillate. So if we just look at the difference in between these two, and then we plot them, relative to the red fitted line, which we don't really have to do to show that there's a gap, but or another phase. But it's slightly easier to see it in that kind of graph. Now you see it looks much more convincing. And in fact, other things that we have done suggest that there is this other phase in between, which is a gapless spin liquid phase, but it exists only in a very narrow regime. Now, the thing is, we have also done, these DMRG calculations for that system on much larger lattices, which we actually did first. And I will not have time to discuss those, but I can just tell you that those already gave pretty much the same numbers here, even though the cluster geometry is different and the clusters are much larger. And this calculation was more like saying, well, could we even possibly see that in the very small lattices? And we were kind of surprised that the results agree so well. And there's some later papers already that seem to confirm this in some other calculations as well. Okay, so now I went 5 minutes over, but I guess we can take only a 10-minute break, and then I will start a new topic when we come back. All right, see you then. Or should we take some more questions? But we had a lot of questions, right?
Okay, then
All right.
Let's take a break.
Yep.
All right,
Okay,
let's
so we-
start again, and
Yep.
perhaps we can stop at 5.
Yeah. Right, sounds good. Okay, so now I'm going to, so sorry, this part was a little bit fast, but if somebody is interested in more details, I can, we can meet in private and talk about it. Anyway, it's something that I also will come back to for those who are here during the conference week. In my talk there, I will talk more about that. Let me just say that, if you are interested in doing some exact diagonalization, but you don't want to write your own code, my former student, Phil Weinberg, and another former BU student, Marin Bukov, who's now in Dresden, he works for a quantum computing company in Cambridge, Massachusetts, I should add. So they have developed this open source software that apparently people like a lot. I haven't used it myself, but apparently it's quite user friendly and so on. So I just wanted to mention that. Okay, so now we have finished this part, and what I advertised was that next I will talk a little bit about matrix product states and things like that. And then quantum Monte Carlo methods. Now, the time, even if it's like 5 days and, two lectures, it's not enough to talk about everything. So, upon, more close consideration and seeing how things are going in terms of time, I decided to not do that because what we can do to most closely connect to CFTs and things like that and look at critical exponents and scaling, we do that with quantum Monte Carlo anyway. So I think it's more important that I talk about that. And in addition, I decided to, instead of brief intro to classical Monte Carlo, sort of maybe believing that many of you have done Monte Carlo before, but maybe not so many have done it. So I decided to basically use some slides from a computational physics course that I teach often at BU. I sort of took some of them and rearranged things a little bit to make it coherent for hopefully not more than maybe today and a little bit tomorrow, to make it easier to understand what we then do in quantum Monte Carlo. So let me just ask, so who has done any type of Monte Carlo simulation in the past? Okay, at least probably half of you. Okay, that's good. But then for those of you who have not, I think what I'm going to talk about now should be enough to at least for you to get the point, what is done. So now, this next sort of chapter, which probably will be all we are going to do today, tomorrow, and on Friday, will be on Monte Carlo and first classical, and then some flavor of quantum Monte Carlo. So let me talk about the Icing model. So we have already heard in Andreas's lectures, the first lecture, he mentioned the Icing model and how you coarse grain it and all those things. So today I want to discuss things in the context of the 2D Icing model as well. But we can use this for many other models, so it's not limited to that. And of course, the 2D case even has an exact solution, so we don't really need to, but it's a really good illustration. And I will be able to even really connect to what he talked about, the free energy and all that. One can actually get such things out of the simulations. I hope you will be able to see how closely connected in some sense these approaches are. So I think you know what the Icing model is, so I don't need to spend a lot of time defining it. In general, you could have some even random couplings here, but I'm going to just study the ferromagnet where it's just J is -1 everywhere, let's say. So the ground state is ferromagnetic. And that Icing model itself has a lot of applications, but now I'm going to illustrate Monte Carlo simulations with it. So let's, well, I also had this slide, but you know what happens, right? As a function of temperature in the thermodynamic limit, you have a phase transition, and this onset of the magnetization is defined by a critical exponent that gives you a power law. It's actually much steeper than what I show here because the exponent is 1/8. So this is just a rough illustration. And the order parameter is the magnetization, which is just the mean value of sum of all the spins divided by n. Sometimes I use little m for the size normalized and m for before I normalize it, so it's not completely consistent in that sense. Anyway, as you will see, this kind of behavior where it's really 0 above Tc, you can only see in the thermodynamic limit. And furthermore, if you really look at m, like not its absolute value or square, but strictly speaking, m itself, the expectation value is 0, right? By symmetry. So when we do, and it's in the thermodynamic limit, you can break the symmetry and m will not be 0. But when we work on finite lattices, we want something that is equivalent to the symmetry broken m in the thermodynamic limit, but has some sensible form also for finite size. So then we can look at m squared or the absolute value of m instead. So what do we do with Monte Carlo in Monte Carlo simulations? Well, so first let's look at this Statmac problem. So the energy could be just Ising energy or something else. S is just a shorthand for all these n spins on some lattice. And we have these 2 to the n configurations. Okay, so we can never sum this up exactly, of course, if n is large. So then you could say, okay, let's do sampling. So the easiest way to do sampling is just to generate these spins completely at random. You just generate configurations. And instead of summing over everything, you just sum over, let's say, 1 million of them. So that should be some estimate, right? If you just sample the population of spin states. That works well at high temperatures, right? In particular at infinite temperature, where all the configurations have the same weight, right? E to the minus E over T. When T goes to infinity, it's all the same weight. But when you go to low temperatures, there will only be a very, very small fraction of all the spin configurations that even contribute significantly to your, to your partition function and to your expectation values. So in particular, if you go to the extreme case at 0 temperature, we know that only 2 configurations contribute all up or all down. But if you draw samples at random and n is large, you will never draw those, right? So you can definitely evaluate these sums based on your finite sample. But your results will be completely wrong because your sampling cannot, in practice, reach the important configurations. So that's why we do something called importance sampling, where instead of drawing them at random, we use some mechanism to draw them in with probability proportional to the weight in the partition function. So in particular, if we manage this at 0 temperature, we would only draw the all up or all down states. And of course, the probability distribution, for any other temperature should be the Boltzmann distribution. And the question is then, how do we accomplish that? Well, the solution is what's called importance sampling. And I'm going to tell you about how to do that. And this will be quite general, not just for the Icing model, but for pretty much any case. I still use S as my symbol for configurations. So it's S denotes configurations in some configuration space, but let's have the Icing model as an example to make it more concrete. So if I really want to write this as a probability, then you can say that, well, the probability of a spin configuration is what we call the Boltzmann weight divided by the partition function. You don't know what the partition function is. You know what this factor is. That's very easy to calculate for a configuration. But luckily, we never need to know Z anyway. We only need to know ratios of probabilities where Z drops out. So if we do sample configurations at random, which I strongly advised against a moment ago, but let's say that we do that, then your expectation value of A would just be the probability weighted function. So this would be some function defined on the configurations, like magnetization squared, for example, divided by the number of the configurations. But then I told you, well, that's a bad idea. So in importance sampling, we already take the probability into account at the stage of sampling the configurations. So we have already weighted them at that stage. And then our expectation value is just the mean of this function evaluated in those configurations that we picked. So I hope that's clear. I still haven't told you how to do that. Okay, so how do we do that? Now, like we always do in statistical mechanics, we imagine that we have an ensemble of states. So the way I think of that is that I have, in front of me some, configurations of spins. And let's say initially they are all random. So I have a gazillion, random spin configurations. And so that's my at my time n0. So I can say, okay, well, I just told you that they are all random. In practice, that could be, but let's say it's not like that. Let's say for some magical reason, these gazillion configurations are distributed according to the Boltzmann probability. So at low T, there's more of the configurations that have a lot of spins in the same direction. And now I'm going to think about, this as a time, or sort of a time step, or some step in a stochastic process. So now I'm going to take all of these configurations that I have in front of me, and I'm going to, according to some rule, make some small changes in all of them. For example, flip a spin in each of them at some randomly chosen spin, but flipping according to some certain rules that I haven't specified yet. But something is done. So then, for a given configuration that I call A, in the next step that could go into B, C, or whatever, but maybe it cannot go into all possible other configurations, but maybe to some limited number. It doesn't really matter at this stage. So then you can say, well, we call that whole process the update. So then you can ask, after I have done that, how many configurations do I still have with the label A? Well, that's what I started with, and not. And then there are some configurations that become A, that initially were something else, but now they become A. And that number is, summing over all that are not A, how many of those I had times the probability of those going to A. So there is some probability P, B to A, which I haven't specified, but eventually that will be, dictated by the rules I come up with. Okay, that's how many more I got, but then some of them also vanished from A. And that's how many I had in A times the probability of A going to B, right? So that's all under the same sum there. So this is something quite general in stochastic processes, and it's called the master equation, all right? So if initially I had the correct distribution, then of course I want to stay in that distribution. So what does that mean? It means that, this thing should vanish, right? So that's the condition to stay in the same distribution. And now, I thought about it as, an ensemble with many configurations, and that's why I have these n's here. But I can just replace that with something that is proportional to that, namely just the probability of being in a configuration, right? So then you have this sum of probability of something in B times the probability of the transitioning into A, and the probability of A times that transitioning to that other B. So those have to vanish. Okay, well, that seems pretty complicated because this sum in principle has, a huge number of terms. And in principle, that should mean that there's actually a lot of solutions to this master equation. But we don't need a general solution. We just need one solution. And we can at least, as a first step, choose the simplest solution, which is called the detailed balance solution. And that means that, this sum is not just satisfied as a whole, but each individual term satisfies the condition. So for any A and B, this should be true. Then of course it's true for the sum as well. So if we have a stochastic process with that probability, we say that it's detailed balanced. Okay. And now I told you that, well, now I assume that for some magical, well, maybe I said it in the previous slide. So for some magical reason, the starting configuration, the ensemble was already in the right distribution. But typically I would start from something random. So now you can see even from this equation here that if initially I have too many in A, when I have done an update, I will decrease the number of A, right? Because I have too many, that means P of A is too big. So let's look at it here instead, or even here. If I have too many in A, then N naught is too big. So that will likely, decrease A, because also, if I have too many in A, I have too few in B. So this is also less than it should be. So it's sort of clear that if I'm not initially in the equilibrium distribution, where, by the way, P is given, right? This is, in our case, the Boltzmann distribution. So these are yet to be specified, but they have to satisfy that. So it's pretty clear that even if I'm not in equilibrium, I will get toward equilibrium if my update rules, PA to B satisfy this equation. Right. So now, like we always do in Statmac, you can talk about an ensemble, which sort of means that you imagine, many of these systems sort of in parallel, and you can talk about distributions and how they evolve. But then it's also a fact that even if you have only one and follow it, only it as a function of time, the whole series of configurations as a function of time will have the same statistical properties as the ensemble at a given time, if you are in equilibrium. So this should, as long as my single Monte Carlo simulation satisfies the detailed balance condition, I will generate the distribution. Well, there's also another requirement, which is sort of obvious, but it should be stated, that in that updating process, I have to be able to go from any configuration eventually to any other configuration. I don't have to be able to go from any to any in one step, but using many steps, I have to be able to. So for example, in the Icing model, if we decide that, okay, our changes that we make are going to be just flipping individual spins, then you see that, from a given configuration, I can only reach n minus one, well, n other configurations, right? But if I repeat that many times, then I can, in principle, get from any starting point to any other configuration, right? By flipping many spins. So that's called, well, I guess everybody has studied some statistical mechanics, so you know that that's called ergodicity. So under those conditions, our process will generate, as a function of time, an ensemble which has the correct distribution. Okay, so let's write the detailed balance condition in some other way, because if we take specifically the Boltzmann distribution, the probability is just that. And then we can just call, this factor here W. And then you see when we take ratios, Z drops out. So what was P of A divided by P of B? If you just divide, you can divide by P of A and P of B. And then you can see that Z cancels, so it just becomes that. So for a given model, we know these W's, right? But we have to specify the transition probabilities so that this condition is fulfilled. Well, at first sight, maybe that seems difficult, but it's actually very easy. So first, we can think of the transition probability as made up of two different stages, two different probabilities. So, for example, when I take my spin configuration and I flip a spin, well, the first stage is I pick one out of n spins, and most natural I would pick them with equal probability, right? So the probability of picking a specific one we can call P attempt. Okay, so B, A is the configuration I'm in, and B is one of the configurations where one spin is different. So I have flipped one spin. So the attempt probability is just going to be 1 over n. Okay, but with that, we will not satisfy the detailed balance condition by itself. We also have to consider an accept probability, by which we mean once I have selected my spin, there must be a certain probability to actually flip it or to decide not to flip it. So that we call the acceptance probability. So that's what I explained, right? So if we don't accept, meaning we actually flip, we think of that as reject our update, and we stay in the old configuration, which is here called A. So again, I already said this as well, but let me say it again. So in our Icing model, first we use, for example, our random number generator. Which one should I pick? Okay, let's pick that one at random. So now we have we had an attempt probability 1 over n, and we happen to pick, this particular one. So we could call that, B, and with an index here, but it's not so important. That's our configuration B. Okay, and then we have to actually flip it, make it from red to blue with some probability that we will discuss that satisfy, this condition that we had. So the attempt probability is uniform in this case. So the detailed balance condition is just involves the accept probabilities. Now I did want to talk about the attempt probability as well, because it turns out that in some cases, especially when we go to quantum Monte Carlo, it's not uniform. The configuration space is more complicated, and there's some imbalance in how you do the updates, and that has to be taken into account. But in this case, it's easy. In the end, we pick them uniformly, and we have to have a condition on the accept probabilities only. Okay, so as I said, it's easy. So there are many ways to satisfy that. And these are probably the two most famous ways. One is called the Metropolis Algorithm, after a paper from 1953 by Mr. Metropolis, who was a group leader in Los Alamos labs in the US. And two authors with the name Rosenbluth and two authors with the name Teller. So it was Metropolis, Rosenbluth, Teller. And one of the Tellers, I think the last one probably, is quite famous because he was also the father of the hydrogen bomb, right? But he was also on this paper. And evidence is that all the work was done by Rosenbluth, except the other Teller, Edward Teller's wife. She apparently actually programmed the computer to do it. And in her honor, at some point, there was a computer language called Ada, because her first name was Ada. Anyway, so Rosenbluths were also a couple. Anyway, so they suggested, not for the Icing model, but they looked at some models of a liquid, is that, well, if you just choose the accept to be the ratio of these two weights, but take the minimum of that and 1, then you can very easily see that if you, divide, if you put that in, this is obeyed. And that's because if this ratio is less than 1, well, then, that you use that for the probability. If it's larger than 1, you use 1. So trivially, that is satisfied. An even more trivial way is, if you take this one, then you see immediately the ratio of them, will be that. So that's called the heat bath algorithm. And it doesn't really matter so much which one you would actually use in practice. And now the point is that these ratios are very easy to study. Yes, please. Okay, but you are going to make them related by spin flips, because that's your algorithm, right? Your recipe is that I, pick a spin and then I flip my spin. So this is well, okay. So if you cannot reach them, the probability is always 0, right? If you say, okay, B is a configuration with 2 flipped spins, well, you never reach that in this process. So, maybe you could say that, this attempt probability is 0 in the first place. So then, the condition is also satisfied if you go to the previous page, right? So you construct your way of updating in a certain way, and you only need to then say, okay, only the B's that are among the possible choices, those are the only ones that you need to care about, because if the probability, for all the other ones are 0, the condition is satisfied. If you go to, I mean, here it may look like, oh, maybe you get some 0 divided by 0 or something wrong. But if you go to the previous slide before we had removed the attempt probability, then you see it's okay, because the attempt probability will be 0 on both sides. Do you agree? Yep. Okay, good. So the point then is that these ratios are actually easy to compute, because when I flip a spin or do any other sort of local update, the weight only depends on the energy, and the energy change, the ratio depends on the energy change, and that's completely local here. So it's easy to compute. So basically the algorithm is select the spin, calculate the change in energy from which you get the ratio, from which you get the acceptance probability, and then you generate a random number. In the computer you can generate a random number between 0 and 1, and then you say, okay, if the random number is less than the probability p, then you've actually flipped the spin. If the random number you have is larger than p, then you stay in the old configuration and just generate another spin, and you just repeat that many times, millions or billions of times. So this is just how you in practice compute, well, how to see that it's easy to compute that, because the weight is the Boltzmann probability, which factors in this way. So when you take the ratio, only everything cancels out except those containing the flipped spin. So in the end, it's something where you just have to sum over your neighbors. All right. Okay, now since it's late, let's have some fun and look at some movies. So here, I have visualized, and by the way, I made these, but you can find, thousands of others online where you can, put in the temperature and system size and play around. But here I just made some illustrative examples. So this is a case where the temperature is 4. The critical temperature that we know below which the system orders is around 2.27. So here the temperature is high, so this should not be an ordered state. And what I didn't talk about in detail, and I will not, but we start with a random state. So then it takes some time before the system actually can reach typical configurations in the Boltzmann distribution at the temperature we have. So here, this is sort of a random configuration, and this will be my time step. So in each, what I refer to as a time step, I attempt n different spin flips, and n being the number of spins. Here the number of spins is, I believe it was 128 squared, or is it 64 squared? I'm not sure. I think maybe just 64. So red and blue, of course, and there's small squares here, so it covers the lattice. But red and blue, of course, correspond to up and down. And now I did start from a random configuration, but I already did n update attempts. So I already generated n random spin flips and used the rule. And now I will run the animation, and this number will increase. So I plot my configuration after each step, and then we can see what happens here. So you see that at this temperature, I reached equilibrium almost immediately, and these look like very disordered configurations, and we would call that a paramagnet. So nothing too exciting happens here. So let's go to lower temperature. This is at 2.3, which is slightly above the ordering temperature, which is around 2.27. So, for all practical purposes for this animation, we are going to be at the critical point, which is, described by a conformal field theory, right? So Let's run it. And now you should be able to see that it takes some time before I get some configurations that represent the equilibrium. And we know that at a critical point, we will have, basically, if you think of just Icing model that we study here, we will have clusters of all system sizes. We have critical, power law, correlation functions, and so on. And you can see here that we have, system spanning domains even, but it's not ordered, right? Here it's like, maybe two big domains and some small domains. So that's characteristic of a critical state. Okay, let's go to. Okay, so here I just speed the movie up just to get more examples of these critical clusters. Here you see that each frame is after 10 sweeps of updates. So here you see that these you really have a lot of fluctuations, right? A lot of different configurations are important in the partition function, but they all have big clusters and small clusters as well, right? It's scale invariant. So if you really did a big system size and you take a snapshot and then you zoom in at all scales, it would look very similar, not identical, but very similar. So it's scale invariant. All right, let's go below the critical temperature. Here T is 2, which is already far below in some sense. It's already going to be ordered. But now you see initially it's not ordered because I start from a random state and it will take me some time to reach the typical configurations, which here would mean mostly blue or mostly red. But now you see that something is happening here. It's not equilibrating very well, right? This is still two big domains there. So let's speed up the movie a little bit. So again, now it's going to be each frame has 10 full updating sweeps between them. So now you can start to see that this red domain is starting to go away. And eventually you just have the big blue sea and some small animals there swimming around. And of course, it was just by chance that I got blue instead of red, right? If I repeat this many times, half of the times I will get blue and half red. And this is really how symmetry breaking happens in practice, right? Because once you have reached these configurations with these local updates I'm doing, it will basically take forever, or at least the lifetime of a graduate student to flip it from blue to red, right? So symmetry breaking in practice is always associated with a time scale that becomes so large that something never happens, and I will illustrate that more in a moment. In fact, now. So that was looking at the whole configurations. Let's instead look at the time series of the magnetizations. Magnetization is again the mean spin value. Spins plus minus 1 sum over everything and divide by n, so it's something between -1 and +1. So the movies were for a pretty big system, 64 squared. Here is for 8 by 8 and 16 by 16. So you see that here, this is actually not too far below TC, but you can already see that it's basically should be characterized as ordered, because the fluctuations are around 1 and -1 mostly, but occasionally the fluctuation is big enough to flip the magnetization from positive to negative. And in fact, this is like my configuration number divided by n. So these numbers would correspond to the natural time unit in the simulation, which is one time unit is n spin flip attempts. So you see that here the reversals happen quite frequently. If I go to L equals 16, I think you can see that they happen much less frequently, and also these fluctuations that don't lead to reversals are typically much smaller. It's much harder to reverse. And in the movie we saw that, well, we can expect that it would take a very long time to see reversals. Yes, please. Yes, roughly. The time scale diverges exponentially. In fact, as I mentioned, these slides are for a course I've been giving, and sometimes I give homework to study that time scale, so you can, define some sensible, way of measuring the reversal time, and just, look at that as a function of the system size. So if you are in the ordered phase, and it's an exponentially divergent time. Okay, so that's the time series. What we may also look at is just the distribution of the magnetization, and this is where we can connect to what we heard in Andreas's first lecture. So let's just look at this picture first. So this is the magnetization distribution. So if I go back, you see this is L equals 16. Oops, so let's go back here. So this is from the same simulation as here. You can see that the fluctuations are mostly of values, pretty close to 1 or pretty close to -1, but there are these excursions occasionally to small, values pretty close to 0, and sometimes when it goes close to 0, it manages to flip. So now the distribution is like collecting all this data for M in a histogram. So these are some examples of histograms in the ordered and in the disordered phase. So in the ordered phase that we just looked at, this is the red curve here. You see you have these, rather sharp peaks correspond to those fluctuations close to ±1. But you have a little bit weight in the middle still. So there's some probability of being here as well. And that also means that there's some decent probability of the magnetization to reverse. But if we go to L equals 64, which I think was the case in the movie, although the temperature may not have been exactly the same, there you see that these peaks are much sharper. Now you have almost no weight close to 0, which means that with these local updates that I do, which can fluctuate, at each step, the magnetization just by 1/n basically, it will never be able to go from here to here because there's too little probability of being there. Now, the interesting thing is that this magnetization distribution here is really directly related to the free energy that Andreas talked about. So you can easily see that, except for a factor, this probability as a function of M corresponds to exactly the free energy as a function of M as well. So the probability, as he talked about, he did coarse graining. Here we don't do any coarse graining, but the process of computing the average M is like a coarse graining, right? To coarse grain over the whole system, and which he also effectively did, right? He just did a first coarse graining step just to have, some essentially continuous values of M, and then looked at the fluctuations of those when he went to the Ginzburg-Landau and so on. Here, I just look at one big system size and say, okay, what's the probability of M? And just from the Statmac, in the Statmac, if you think of coarse graining over the whole system, you have, for each magnetization, you have many, many configurations, right? So you have a big number of configurations for a given M, and then you have an internal energy which is used to weight the configurations. So the total weight of a given M sector is, that e to the minus e divided by t times the number of configurations in that sector, right? And, the number of configurations, the log of that is the entropy, basically, right? So this really is exactly true. You can extract the relative free energy from these curves. And you see then that this corresponds to 2 free energy minimas. Whereas if you are above TC, these black curves, then you only have one peak in the M distribution, which means that you only have a free energy minimum at M equals 0, right? And then, of course, the really interesting thing is what does the distribution look like at the critical point, which I didn't draw here, and that has some universal properties, which are, related to, critical exponents, which are related to the scaling dimensions that you have heard about. So, for example, the width of the distribution at criticality depends on the system size exactly according to those scaling dimensions. I will talk about that more when I have talked about quantum Monte Carlo and how to analyze the data and connect to RG. All right, so now I will not say much about this thing. I just kept the slide because it talks about other things that you can calculate. So in the end, normally you compute expectation values, right? For example, of M squared, but you may also be interested in other quantities like the internal energy or the magnetic susceptibility. So this is just an illustration of how you derive what's called estimators. So if you think of the magnetization, just the original Statmac form of it, the susceptibility is the derivative, and now I have included a field here, right? So we start with the Icing energy without field, and then we add a field, and then the susceptibility is the derivative of M with respect to H, and we can consider it at H equals 0, right? So then you just take your Statmac forms, and you can carry out the derivatives of in these forms, and you get two different terms eventually. There are some subtleties here that let's not discuss, but basically the susceptibility is the magnetization fluctuations. And here M is actually the total magnetization, not divided by N. And the specific heat will be the energy fluctuation, right, with some factors in front. And we can compute correlation functions. Of course, those are really interesting when we want to compare with some CFD predictions. So let me just show you one result, and I will discuss more about it, how you analyze such results later.
Question?
Yeah.
So when you do these averages, which spin configuration do you choose? Like you keep all of them, or it's not,
you keep all
your
the ones
first
that,
thermal?
no, you keep all of the ones that you generate, except, as you saw in those movies, successive configurations look sort of similar, right? It takes some time before they become statistically independent. So there's nothing wrong with averaging over every single configuration that you generate, or after each step of N spin flip attempts. But sometimes that's wasteful because they are not statistically independent of each other. So sometimes you say, well, maybe my, as we call them, measurements, if they are very time consuming, you don't want to do, you don't want the measurements to take more time than the actual simulation. So then maybe you decide, okay, I'm going to only measure after every 10 steps or something like that. But it's never wrong to, you will not get the wrong result if you measure always. That's still a completely unbiased way of doing it.
You don't need to throw away the first one.
Okay. So initially you should throw away some things, right? Because initially, if you start from a random configuration, a fully ordered configuration, whatever, initially the system is not in equilibrium. And that sometimes can be an issue because in some cases that can take a very long time. So you should wait until you get typical configurations, and you in some cases have to be careful and really monitor that. So you can do it, and check how things converge as a function of time, for example. But from the movies, you pretty much could see, especially the one in the ordered state, that initially, it looked nothing like an ordered state, and eventually you just had some small animals in the sea there, and there's no reason to expect those to not be equilibrated. Okay, so let me show you some results here, and I think that's going to be all for today, so the timing is pretty good. So here I show the squared, normalized magnetization as a function of the temperature for several different system sizes. So now if we look at, and we know, by the way, that the transition, which strictly is defined in the thermodynamic limit, should happen around here, 2.27 roughly. But for L equals 4, this curve is very smooth. There's no sign of any phase transition really there. It looks just like a smooth crossover. But as you increase the system size, you see that these curves really start to fall on top of each other and form this quite steep drop here. But for any system size, there's going to be some rounding here. So 128 is not super big. You can go to much bigger, but at least you can see that you start to develop what eventually will become the singular power law onset of the magnetization here. But to really see, the fully singular behavior you can never do, because you would have to go to infinite system size. But what you can do is to analyze the data in various ways that I will talk about later. Analyze your data close to the critical point using what's called finite size scaling. And this is strongly connected to what we have heard about CFTs. It doesn't have to be CFT, even just a scale invariant critical point, where the RG formalism predicts how you relate results for one system size to another system size, which is also exactly what Andreas talked about, but in a completely different language. Right? But he talked about how to rescale behaviors from between different system sizes, or at different scales. You could say, okay, I have an infinite system size, but I look at it on different scales, like compute things in a small patch or a bigger patch, or at different energies, whatever you like. So finite size scaling will do that and allow us to extract the power law governing this behavior, even if we only have finite system sizes where there's always some rounding there. Okay, so now the timing is perfect, so I will end here, and then tomorrow I will just talk a little bit more about classical Monte Carlo, maybe 10-15 minutes, and then I will switch to quantum Monte Carlo. So thank you.